Okay. All right, thank you, ladies and gentlemen. And now, please welcome Nina Raqueno. Nina is a research scientist with the Digital Imaging and Remote Sensing Laboratory here at RIT's Chester F. Carlson Center for Imaging Science. And for the past 19 years, she has performed the thermal calibration for the Landsat suite of instruments. And over these years, this effort has required much field work, and her position evolved into the DRS Field Campaign Coordinator, assisting DIRS students, faculty, and staff with their spectral measurements, requirements, and logistics. Nina's presentation title is 1999, Spectral Odyssey and Beyond.
So you can tell that I took this very seriously. I had a presentation set up, mostly on Landsat. And then I saw that I was the last presentation of a very long day. And I said, you know, we're going to change this up a little bit. Oh, excuse me. See, it doesn't matter how many times you try things out, huh? We're going to change things up a little bit and talk a little bit more about the future. I'm not going to go all the way back to 1999, but I am a little bit. I'm going to do what you never should do. I'm going to actually read a scenario to actually kind of set the stage. But this journey actually began back in 1999 when we received our first ASD. We immediately took it out within days, like within 2 days of receiving it, and took it out on one of our largest collects under Avarice. We were very lucky to get a hyperspectral sensor overhead over Lake Ontario waters, and we went out and used it immediately with some success. And given the 2-day training, I think we did reasonably well. Back then, receiving the ASD back in 1999, it really was a sci-fi event. We really thought we had an absolute marvelous instrument that we thought we could do absolutely anything with this. And I immediately, I did not participate in that collect with the instrument, but within 2 days after that, we were out at Gannett Nuclear Power Plant measuring spectra with the ASD, and that's where I became one with the ASD. And we've ever since then we've been connected. Basically, because I found out that not all rocks are rocks, and I slipped and I fell into the lake. ASD was up here, though. From that day on, ASD knew that I was going to take care of it, no matter what happened. things would be okay with it, whether it meant that I was still alive or not. I would take care of that. So I'm going to start off this conversation with a little scenario, a little sci-fi scenario. It's just one example, but I want you to think about your own application, whether it be volcanology. We've already seen a great example for architecture. I'm going to talk about one scenario, and as I go through this and read through this, I want you to think about what we actually can do now, what we can't do, throw stones at this scenario, and what it's actually going to go ahead and take to actually get to that level. So I'm going to do what everybody says not to do. I'm actually going to read this. So students, don't ever read in your presentations. I'm not a doctorate, so it's quite okay. So it was a beautiful fall day in the Finger Lakes in western New York, as a lake resident finally dropped her canoe in for one last paddle. One last paddle of the season. This is Canisius Lake down just south of here. As she was paddling along, she noticed that the water looked kind of odd. Now, she doesn't know much about water, but it just kind of looked like somebody had spilled green paint all over the waters. She had just recently signed up to be a volunteer watershed monitor, and she really wasn't sure what that was. Training doesn't start until next spring, but she downloaded the app to her phone and her watch, and she went on and she fired a couple pictures up. So she took these pictures with her little watch, and they were immediately linked up to a local monitoring system. She really didn't even give it a second thought. She really didn't know what she was doing. Again, she hadn't been trained. She didn't think about it for the rest of the day, and she didn't need to, because the location and the photos are automatically uploaded to the DEC lake monitoring system. So this monitoring system is in a constant state of modeling all the state's water bodies. It ingests satellite image. It is, as we probably have seen quite a few today, local weather conditions, forecasts, reports from citizens, and all sorts of watershed investigators. The model earlier that week indicated that the conditions were ripe for algal blooms in several of the western New York regions. But so far, no confirmed reports had materialized. So when that lake resident fired up the monitoring system, took those photos, the system was already in this kind of a state of alert. It was looking for any kind of harmful algal blooms. The images she took were no ordinary images, for the app knew exactly what specific wavelengths that would aid the identification of different water constituents, algae, and even cyanobacteria. The system immediately performed spectral analysis on those images, flagged a suspicious case of a toxic cyanobacteria indeed, and it indeed found that there was probably Microcystis present. But that was just one report, just a single report from already acknowledged, uninformed, untrained observer. The real question is that whole lake actually in a state of harmful algal bloom? The monitoring system needed more information, so of course automatically it turned to the latest satellite image. And as we've already seen and talked about in this previous talk, pretty much cloud covered throughout. And the lake that I'm talking about is right here, Kinesis Lake, one of the Finger Lakes. Furthermore, it actually went ahead to see what the next scene was going to be available from any of the satellites. And there indeed was going to be a satellite image later that afternoon. But coupled with local forecasts and modeling systems, it deemed that there's probably only going to be 25% chance that the scene would be clear. No big surprise. So, the regional DEC water inspector was notified and the drone pilot. Again, just by the system. By the afternoon, the sunlight was dwindling and the drone would only be capable of imaging a few sites, not the entire lake. The monitoring system identified 4 high priority areas, 2 parks, 1 summer camp, and the intake for a local water authority. By the time the drone operator arrived at the lab system, the flight plans had already been uploaded to their system. And furthermore, there was suspicious algal bloom. The drone was actually, drone's camera was actually tuned specifically to those wavelengths, specifically linking to the Microcystis. As the drone operator began prepping the flights, he thought surely he could save time and skip over the flights over the summer camp. This image was taken in late October. Nobody was going to be at the summer camp. He went on grumbling about technology being too smart for common sense, and then he received a text. There was a huge event planned at the camp on the waterfront that weekend. So he set off to deploy the drone with the auto-generated flight plans. Within minutes of landing, the imagery was uploaded to the cloud, mosaicked, and the local RIT Institute applied the harmful algal bloom algorithm that they developed. And immediately, just the map was actually uploaded to the DEC. There was no need for all the imagery, just the product. All they wanted to know was where the harmful algal bloom was occurring. So the map is just showing 3 specific areas indeed where that bloom was occurring, and that one long pond point was actually clear. So we'll go on to skip a bunch of this, but just a few years ago, you can figure that this scenario would be absolutely impossible. But I think today, we're actually getting quite close. With the addition of GIS integration, drone technology, obviously the spectral studies that we've been doing, we're actually getting quite close. Years previously, a report might have come into the DEC from a lakeside resident. They might have sent somebody over to investigate. They might have decided, it looks kind of suspicious. We'll take a couple samples, and then 3-4 days later, they would have gotten a report back. They may have just decided to close the beaches, especially around the camp, excessively, or they may actually just go ahead and just pass it off and somebody could have gotten seriously ill. We're going to talk a little bit about harmful algal blooms, but really the question is are we actually there yet? Whether it's this application or your own, what's it actually going to go ahead and take to actually move this forward? I'm going to talk just about a couple of different projects that we have here at RIT that kind of chips away at some of the problems of the specific example. So one of the obvious things right now that jump out is, okay, so we probably can't detect cyanobacteria with our cell phones right now quite yet. But those images that I showed, go back a little bit. There's clearly something going on in that water. Anybody could actually see just visually what that is, and we can actually fine-tune those sensors very soon. So maybe we can't quite do that, but back in 1999, we were just barely starting to measure the spectra of things, and we've actually come a long, long way. So I'm just going to talk about 3 topics that I think kind of chips away at this specific problem. I'm going to be talking about the Share 2012 Collect. I'm going to be talking about some of our Landsat 8 work that we've been doing, and a project that we just started that focuses more on this specific harmful algal bloom problem. Again, I'm going to be talking very, very high level. Each one of these could be their own couple-hour conversation. We won't have that now. The Share 2012 Collect has been featured at SPE presentations for full sessions. So there's lots and lots of information I can share with you about that. So I actually lied. I'm going to talk about a couple other collects. That's just a quick image. Immediately, I just want to emphasize that we've always been using our ASD for a huge variety of projects, but we immediately started using it specifically for water applications in 1999. We've used it for deer sig simulations, our image synthetic scene model. We've been using it for even crime scene analysis. I'll be just talking just about a couple of those projects. I don't know why, but because we're at RIT University, we have lots and lots of students. Every couple of years, we decide to have a really large collect. Let's just have a whole bunch of students go out, design all their experiments, and see what kind of sensors we can actually fly over that and have them have plenty of data. So one of these examples was Mega Collect 24, and it's called Mega because it was actually feeding Mega Scene for our deer sig data. It had 2 different types of hyperspectral. It had long wave HSI, which at the time was unheard of. Extensive ground truth, probably about 50 different people, probably 10, 15 different types of experiments. Data distribution turned out, even though they were promised to get us the data, it actually ended up being restricted. And we had unbelievable time actually trying to even use the data, and worse yet, publish the data, which is really important when a student's trying to graduate. Again, flash forward to 2010. We tried to do this all over again with Spectier data. And this was data they were going to be able to be in the area, fly over RIT. We did a whole ton of different types of experiments, extensive field campaign, tons and tons of spectra measured with it. And did I mention that it was kind of a freebie? Spectier, actually, they were in the area and they were going to basically do this at cost, just flight time. Awesome, that was great. Not so much. The idea of share was to actually be able to share and release the data to the whole entire community. But unfortunately, the data wasn't quite up to snuff for Spectier, and they did not want us to release the data as their golden data set. So our huge effort in 2010 kind of fell flat when we actually couldn't release the data. We were still able to use the data in-house, but not showcase it as our huge, large collect and data dissemination to the whole community. So the recurring theme here in remote sensing is lack of excellent data sets. lack of imagery and the corresponding ground truth. And so, I don't know why, but we never give up at a university. We decided to actually go ahead and do Share 2012. So just 2 years later, let's try this all over again. But this time we're going to pay for our own data. So a huge expense, we paid for our own Spectier flights, and that way we could share the data to the community at any point in time. It was our own. So Share 2010 or 2012 was just a multimodal image collection with a large field campaign. Had a great graduate student help me coordinate this effort, Anne-Marie. And the main emphasis on this was in the name, was that to make the data freely available to absolutely anybody. So it was organized as a large multimodal collect over Rochester, New York, with extensive ground truth. Provide the community with all of this and actually disseminate the data as well. Obviously letting the students participate in the whole planning process and execution. Here are some of the different modalities of interest. As I mentioned, we had Spectier, so we had a high spectral resolution sensor and a high spatial resolution. We had our own RIT WASP. We had also acquired Digital Globe and GeoEye, all of these sensors on the same day. We also had LiDAR, airborne LiDAR and ground-based LiDAR as well. And we had hoped for full motion video in long wave, and that was just cost prohibitive. Maybe for Share 2020 or something. So the motivation was if we actually had brought all these suites of different types of imagery, will they come? So we actually went ahead and said, this is the list that we've actually have promised. We'll be able to share it. And boy, did they ever come. This is just a small portion of the list of experiments that we did on this particular collect. All the way from human subjects and different types of change detection. There was a Kinesis Lake water object submerged. There was an unmixing, lots and lots of different ones. And the point is there were tons of sub-experiments throughout the entire process. The word did get out. This was an RIT funded project, but the word did get out through a variety of our alumni that this was going on, and so we actually had quite a few partners as well, mostly bringing their own ASD instruments to help us with the ground support and to set up some of their own experiments. And I'm not going to go through any of the experiments. The main point of this is that there was a lot of different types, mostly on land, some in water as well. And this is just showing some of the different sites that we collected on. And the main site gives you just a feel for some of the different targets that we deployed. And some of the variety of different ones that were in the area. So I'd be remiss not to show a single spectra somehow in this, right? So this is just one of the many experiments and some of the different targets that we had out. It was a whole unmixing problem where we built these large quilts, for lack of a better term, of very precisely measured amounts of different colors and constituents patterns. Again, we had extensive ground truth GPS, all the imagery. We had 2 radio sound launches. Lots of in-water samples as well. Lots of ground truth. We had 3 ASD field spec, I believe they're field spec pros at the time. 1 ASD doing full sky irradiance measurements with the RCR for the entire day. And we had very, very large calibration targets. And we took a variety of measurements both throughout the day, both in reflectance and radiance mode for the different experiments. This is pretty much one of my main contributions, rather than organizing the troops, was actually to come up with the system of the data distribution after the fact. So not only is the data all freely available, the imagery, all the ground truth is available as well. And so for any one particular point in this GIS system, you click on a different type of icon, different type of experiment name, and automatically downloads the spectra that was taken from that point and any of all the ground images that were taken surrounding that point. So it's just a system that no matter, you can actually search through all the different types of imagery, but also through all of the ground truth that we collected, whether it be the ground-based LiDAR or the spectra or even the radio sound. So I just put this up there. There is a web page where you can actually get all the data as well. So I'm going to move forward. That was basically making data more accessible and integrated, a key component to actually solving that initial scenario. The present, what we just kind of finished working on primarily is for the Landsat 8, looking at coastal water studies. And I think that's pretty much where we are. A lot of us still are at this point where we're still just trying to validate remote sensing data. It's what we use the ASD on an almost daily basis to do. So this is a project by Javier. He just finished up, just started working down at NASA Goddard, but worked with him for the past 3-4 years on the use of Landsat 8 for monitoring freshwater and coastal waters. Obviously, I'm not going to go through his whole thesis, but what he actually did was actually look at Landsat 8 to actually derive different types of water constituents, so the chlorophyll, the CDOM, the suspended minerals. And not for really easy cases, but for the difficult cases on Lake Ontario. So for coastal waters, really turbid waters. And what he wanted to do was take a Landsat 8 image, see if he actually could produce chlorophyll maps, dissolved organic maps, and the suspended mineral maps. And again, why Landsat 8? We know that this is probably possible for hyperspectral. There's been lots of research. If you had an Abercine or hyperspectral sensor, you could actually do this. But why Landsat 8? Well, for one, we're on the Landsat 8 science team, so I guess there's some money and funding issues. Students like to get paid and they like to eat. So that's one of them. But also because Landsat 8 had a couple of new features. Not so great in the thermal, but awesome new features in the visible. It had a new blue band. It also had, obviously, a really great bit depth, and improved signal-to-noise ratio was the huge factor. And there's just 2 different examples. You probably really can't see in this example the difference between Landsat 5 and Landsat 8 is tremendous for water quality. So his study was basically to look, does this Landsat 8 actually improve? Can you actually start looking at just a few bands and actually still deduce what those different water constituents could be? We studied, again, for many, many years up at Lake Ontario. This is just the Rochester area. And we went through a variety of different experiments. Every clear Landsat day was, we tried an attempt to get out there, basically from May to November for 3 years. We collected data, and he actually basically ended up with 3 data sets out of probably trying about 60 times. So it is very cloudy in Rochester indeed. We collected remote sensing reflectances, water leaving reflectance. We measured that and correlated that with water samples. So we actually did the lab analysis as well, looking at exactly all 3 of those constituents and what the actual values were, so that we could correlate that to the reflectance measurements. We went through a series of revisions and came up with a method to actually take our spectral measurements, and it's really quite comical because you do need to take a very conscious effort of actually making these measurements in very specific angles when you're dealing with water and taking your sky values as well. And when your waves are about 3 to 4 foot in height, those angles may not be quite what you think they are. So we definitely need to come up with some better ways to do that. This is just an example of why we love this area, I guess, despite the clouds, after complaining about all that. These are some of the different sites that we go. We actually split up in a handful of teams, and we trade our equipment off, go out in a large boat out into Lake Ontario, and then some canoes in some of the smaller ponds. But why we really like them is the diverse water types. In one specific day, we can get a huge variety of not only just the remote sensing reflectance values, but all those constituents. So I don't know if you can see, going back to this one, This is actually called Cranberry Pond. It can have a huge, huge amount of chlorophyll compared to any of the other water bodies. Anyways, they're very, very diverse. There's a couple of different reasons we won't go into it, but it gives us a really quick snapshot in one very small area of large different types of water. So I'm not going to talk about his whole thesis. There's references in the slides, but basically what he went through is he came up with a routine where he took the radiance from the satellite, spent a huge amount of effort dealing with all the atmospheric compensation over water, which was critical. Coupled the measurements that we took, the lab measurements, with the reflectance measurements that we took in the field, and used hydrolite to do the predictions. And so he did tons and tons of results, all his results going down to one specific day, one slide. It's not doing it justice, but basically what he did is actually was able to produce these maps. And not only was he able to produce these maps, he's got the ground truth, the spectra, and the lab analysis to actually compare and see how well could he actually estimate the chlorophyll, for example. So it's inching forward. Again, this has been done with hyperspectral. This is just using a few bands out of Landsat. So I just want to quickly go through one presentation that we actually have just started. So this research just started this fall. Student Ryan Ford and his advisor, Dr. Vodacek, they're looking at this problem, exact problem of dealing with harmful algal blooms. I think you've all probably heard of the case last summer, where Toledo didn't have drinking water for days on end, basically because of a huge algal bloom in Lake Erie. Not only is it obviously a huge problem if it's your drinking water source, even if you come in contact with this and you have an open wound, you can actually get a very severe infection. You can also have liver damage. So it's pretty nasty stuff, something that we really need to start learning a lot more about. There's some major types that are found just in this area. The most common is this Microcystis. It's a couple of other ones. Not all algal blooms are toxic, and that's what we're trying to look at. There's a whole series of why they actually cause. One of the latest ones is it quite often will occur right after a really high wind event. It actually is picking up a lot of the nutrients from the water body's floor, and mixing that up. In the late fall, that'll turn into a bloom. Again, not all blooms are toxic. So this is just one, I don't know if you can even see that, but it's a Landsat image. A couple of Finger Lakes in there. Some small regions where there actually are blooms, and actually there are confirmed cases from the New York DEC in these two regions at this time of those areas. And so what he's just starting to look at, again, just started in the past couple of months, looking at Landsat 8 and the cyanobacteria, extending basically what Javier did at the water constituents, seeing what he can actually learn from the satellite imagery. And going back to this image, doesn't take much to see that there's something really going on there, and we actually can see it with satellite imagery. We want to take it to the next step and actually look at it and see, can we look at the factors leading up to that bloom? Can we predict those blooms? And can we actually determine whether or not there's really something actually harmful in them, or are they just an algal bloom? So, unfortunately, we had a very large algal bloom in the north end of Cranberry Lake this past late October. And so he literally just started getting his hands wet and dirty, and actually started going out and collecting some measurements. So we took water samples, as well as obviously we went out and took specific spectra of this. So he's just at the beginning stage, what these actually look like, the different characteristics. This one here is basically all in a suspended mode, and there's just obviously in a much thicker. And he's really starting, as you can see, because he calls this scum. We probably will need to beef up that that terminology. Not too long. Again, we're in just the beginning state, but we actually were able to have a local company actually fly over this area with drones, and so we actually have some higher resolution imagery of this particular area as well. And we are coordinating with the regional DEC to see what kind of timelines they need and what are the exact products that they would actually use if they had them, and what kind of time frame they need those in. So again, my question is whether or not it's this application or your application. Are we there yet? Can we take spectral data and turn it into some kind of real-time system? If not, what are some of the factors that we need to fix? As I already pointed out, obviously we can't go around and scan things quite yet with like a tricorder and say, yes, there's definitely something poison in there. But I think we're getting really close, and I was quite intrigued by this device here. Haven't had one in my hand yet, but I'd like to try this one out. The ASD's very small, portable quality spec. Might be something good size for water regions. But I think quite often most of us are kind of still in this stage, and we're still kind of looking at the spectra and kind of scratching our head what we're actually looking at. And hopefully we'll get past that. So that is it. My contact information, most of you know who I am. It's just Nina at here. And I'd like to also thank that many of our students have actually been the great recipients of the GETS instrument program. We've actually had loaners quite frequently. They don't always line up with the exact customs problems and the cloud problems, but we've actually been very fortunate to have our students be able to have some extra ASDs here at the university when we were really tight for projects. So thank you.
All right, ladies and gentlemen, thank you again for attending the event with us. If you'd like to learn more about the various application uses for ASD instruments or other specific applications as pertaining to our use, we have a webinar series this year. It'll have a new webinar every month. You can go to our ASD events section on our website at www.asdi.com, and you can register for those events as they appear. If you have any ASD related questions, please contact us via email at nir.info@panalytical.com. Thank you again for attending, and this concludes the event.